we're going to keep looking at trig ratios, and this time we're going to look at how do they look when we have similar triangles. Again, similar triangles are not congruent. We don't have all the same side measurements, but they're similar. Okay? In other words, the sides are proportional. We're going to look at what happens to trig ratios when we have that scenario. So I start here with two triangles, triangle ABC and JKL. And I started with just a little bit of review. If we know that we have angle A and angle C that were identified, we know that C is the same measurement as L. We know that A is the same measurement as J. So if we think back to last chapter, we know that we have an angle-angle similarity. Therefore, the sides are all going to be proportional. Okay? And I set up a little deal here. We know that 6 is going to correspond. The side of length 6 is going to correspond to the side of length 3, and the side of length x is going to correspond to the length of side 4. We can see from this, we cross multiply and solve that x equals 8. So we have two similar triangles. The sides are all proportional, but they're not identical. So we're going to look at what do trig ratios look like in that type of scenario. Okay. I've copied down these triangles again, and I also went ahead and calculated the lengths of the hypotenuse. Used the Pythagorean theorem to do that. You should have plenty of work on that by this point. So, let's start by comparing the sine of angle C to the sine of angle L in these two similar but different triangles. Well, our sine of C, sine is the opposite over the hypotenuse. Opposite is 6. Hypotenuse is 10. We have a fraction of 6/10, we can reduce that to 3/5. All right, let's find the cosine. Cosine, adjacent over hypotenuse. Adjacent is 8. Hypotenuse is 10. That reduces to 4/5. Finally, our tangent. Our tangent is the opposite over the adjacent. Opposite over adjacent. 6 over 8. And that reduces to 3/4. Okay, so we've got a set of trig ratios now for one triangle. Let's compare them to the similar but different triangle. So we're going to look at angle L. That is the corresponding angle to angle C. L, the sine, is the opposite over the hypotenuse, or 3/5. We can't reduce that any further. Cosine is the adjacent over the hypotenuse. Adjacent is 4. Hypotenuse is 5. So cosine is 4/5. The tangent of L, the opposite is 3. The adjacent is 4. 3/4. Notice what we have going on here. The sine for these two angles, remember, angle C is going to be congruent to angle L. Angle C is congruent to angle L. Notice that the sine ratios are the same. The cosine ratios are the same, and the tangent ratios are the same. Now, I could go on and keep doing this for cosecant, secant, cotangent. I could do it for angles B and compare it to angle K. They're not going to be these exact numbers, but those are going to correspond. Okay? I can see that the cosecants, the secants, the cotangents all correspond. Rather than go out and do that, I think this gives you the idea of what's actually happening here. So, if we know the trig ratios for one triangle, we know them for similar triangles. It also means this important fact. That trigonometry ratios are constant for a given angle measurement. So, if we have the sine of an angle, let's just say we had the sine of angle, let's just say we had this one of angle B and it was 30 degrees. Whenever we compute the sine of an angle that's 30 degrees, we're going to get the same answer. It could be 30 degrees. All the sines of a 30-degree angle are going to be the same. All the sines of a 45 are going to be the same. 60, 70, 75, 92.38, all going to be the same regardless of what triangle we're looking at. So they're going to be constant. We can also use this to find trig ratios for maybe angles we don't know, but we know them for a similar triangle. Let's look at this example. We have a big triangle, ABC. We have a smaller triangle within that, DEC. Notice that we have angle-angle similarity. Angle A corresponds to angle C, angle D, I'm sorry, and angle C always corresponds to angle C. They're congruent. So, if we wanted to find the sine of angle B, we just look at what angle corresponds and see if we can find that trig ratio. Well, B corresponds to E. So if we can find the sine of E, that'll be the same for the sine of B. So for E, our sine is our opposite over our hypotenuse, 12 over 13. That's going to be the same for B. They're going to have the same angle measurements. They're going to have the same sine. Cosine of B, that would be the adjacent over the hypotenuse of E. And finally, our tangent, opposite over the adjacent, 12 over 5. Hopefully this gives you an idea of what to look for. Also reinforces the concept that trig ratios are constant for a given angle measurement. It's all because of this whole similar triangles. We'll see you in the next video.